Hi, and welcome back to another video on game theory. In this video, we'll have a look at a very special case of bimatrix games, which are called matrix games or zero-sum games. So this section is called matrix games. Now, you remember that a bimatrix game was specified by two payoff matrices, one for the row player and one for the column player. Now, the special case of a matrix game is we only need one matrix because the payoffs are inverse to each other. So whatever one player gets, the other has to pay. So that means one payoff matrix is exactly minus the other payoff matrix. And so it's sufficient to specify just one of these two matrices. We just have to agree on a convention of which one that would be. And this is the definition of a matrix game. So let's start with that. So let's say we have a bimatrix game. And that is specified by matrices AR, AC in R to the m by n. That is called either a zero-sum game or a matrix game. If a R is equal to minus a C. So what that means is the loss of one player is always equal to the gain of the other. This can be used to model games where one player pays to the other a certain amount of money depending on the outcome of the game. A matrix game can be specified by just one matrix, and by convention, we use the payoff matrix of the column player to do that. So, a matrix game, by convention, will be specified by just the payoff matrix of the column player. And this implicitly contains the fact that the payoff matrix of the row player is then minus the specified matrix for the column player. So let us take a moment to see how the payoffs would work in such a situation and how the definition for a Nash equilibrium will work in that situation. So that's a remark. For a matrix game, with payoff matrix A, we'll just call it A now. And again, let that be an R to the m by n matrix. the following holds. First, the column player is still going to maximize the payoff, and the payoff of the column player is y transposed times A times X for strategies Y of the row player and X of the column player. So that doesn't change. So for strategies X in SC, Y in SR, columns payoff is Y transposed AX so column maximizes Y transposed AX. On the other hand, the rouse payoff is minus Y transposed AX, because the payoff matrix for row is minus A. We'll just take out the minus. So you could also say row either maximizes this expression, or you could say row minimizes Y transposed AX without the minus sign. So if you have an expected payoff computed for the column player, then you can also use that for the row player, but you have to keep in mind that row minimizes, column maximizes. So those roles are different now if you use the same expression for the payoff. And second point, Nash equilibria. The pair of strategies X star, Y star in SC times SR is a Nash equilibrium if and only if. What do we need for a Nash equilibrium? First, we need the fact that there is no better strategy if the column player is given the chance to change his strategy unilaterally, and there is also no better strategy for the row player. So we have the outcome for X star, Y star. That would be Y star transposed times A times X star. And then we first need the fact that this is best possible for the column player. That means this is the maximum that a column player could get, given that row always plays Y star. So there's a maximum, and that means Y star transposed AX is less or equal to Y star transposed AX star for all possible column strategies X. So for all X in SC. And for the row player, remember the row player now would want to minimize this expression here. So if a row player changes from Y star to anything else, then the payoff must be higher or equal, not lower. So that means we would also have that this is less or equal to Y transposed AX star for all Y in SR. So this definition of a Nash equilibrium can be nicely put into one single line instead of two different lines, because we only have this one matrix now. Now let's look at an example to see how this really works here. For example, here's a game that's called Parity. And the idea of parity is that row and column play against each other. They both simultaneously show either one finger or two fingers. Then, depending on what they did, one player pays €1 to the other. If both show the same number of fingers, so if they either both show one finger or both show two fingers, then Cullum gets €1 from Rao. If they show different numbers, so one shows one finger, the other shows two fingers, then Rao gets €1 from Cullum. That's the rule of the game here. So let's make a quick note of that. The idea is the rules are Rao and Cullum both simultaneously show either one finger, and we call that strategy 1, or two fingers, and we call that strategy 2. If both show the same number, Cullum wins and gets €1 from Rao. And you notice this is the zero sum fact here, so whatever Cullum gets, Rao must pay, and vice versa. If both show different numbers, Rao wins and gets €1 from Cullum. So what is the payoff matrix? Let's see. Now, both players have exactly two strategies, and they're the same strategies. So Cullum and Rao can both play either 1 or 2. If both play 1, in this situation here, they show the same number of fingers. So remember, in that case, Cullum wins and gets €1 from Rao. And remember, this is Cullum's payoff matrix that we showed here. So A is the payoff matrix for Cullum by convention. So that means in this case here, 1, 1, Cullum gets €1. And implicitly, this also means Rao pays €1. Now in that case, 2, 2 here, that same thing happens. Both show the same number of fingers, so Cullum again gets €1. In the other cases, the number of fingers is different here and here. And in these cases, Rao gets €1, or in other words, Cullum pays €1. So from Cullum's point of view, the payoff is now -1. It has to pay. So this is the payoff matrix for the parity game. And of course, one question that we can ask, and should ask, is there a Nash equilibrium in that game? And how do we find that Nash equilibrium? Let's first see if we can find one in pure strategies, because that might be easiest. To do that, we'll assume there is a Nash equilibrium in Rao 1. So fix that Rao and assume there is a Nash equilibrium there. Either we find it, are we good? Or we can show that there can't be one. And then we have a look at Rao 2. So first assume there is an equilibrium in row 1. Now, if that is the case, let's have a look at row 1. If that is the case, then let's have a look at the column player. Which of those two strategies would the column player select if he knows that row is playing row 1? Well, the payoff for the column player can either be 1 or -1, and of course he maximizes payoff, so he would like this one here. So that means if there is a Nash equilibrium, it can only be here. That point would not be stable for the column player. He would want to change to this situation here. So then it can only be in column 1 as otherwise the column player would have a better strategy. Now, however, if we look at this, so we've decided it can only be in column 1. And if we look at this from the perspective of the row player, then this point here is highly undesirable for the row player. The row player would much rather choose this point here, because -1 for the column player means the row player gets money. So the row player has an incentive to change. And that means this point is not row's best response to column player, column 1, so this is not a Nash equilibrium. However, row will want to change to row 2 if column plays 1, 0. So, no Nash equilibrium. At least not in row 1. Now let's do the same analysis for row 2. So there is no Nash equilibrium in row 1, so let's assume there is an equilibrium in row 2. Again, let's have a look at that matrix. I'll copy that. So we have 1, -1, -1. Now we have a look at row 2. Let's see. Now if we're in row 2, then surely the only possible equilibrium is here, because otherwise, here, the column player will want to change. Then the equilibrium can only be in column 2. Otherwise, the column player will change their strategy. On the other hand, if we are in column 2, then you will notice that the row player in this position is again very unhappy, because he's going to pay 1, and he could get 1 if he changes his strategy to row 1. Again, the row player would not select row 2 if column plays 0, 1, because row 1 would secure a better payoff. So again, no stable point in this row, no Nash equilibrium in row 2. And what that means is, of course, that there is no Nash equilibrium in pure strategies. Another question is, what about mixed strategies? We know for a bimatrix game there is always a Nash equilibrium in mixed strategies. A matrix game is a special case of a bimatrix game, so of course there must be a Nash equilibrium in mixed strategies. So how about that? Can we find that? So let's see what happens here. And that's the next point. What about mixed strategies? Now let's say we have two strategies. We have the row player playing y and 1 minus y, and we have the column player playing x and 1 minus x. Say row plays y and 1 minus y. Column plays x and 1 minus x. With x and y in the interval from 0 to 1. This covers all possible strategies of the row and the column player. Then what is the expected payoff? Well, let's compute that. What we have to do is we have to compute y 1 minus y transposed. The payoff matrix is 1 minus 1 minus 1, 1. And then x 1 minus x, like this. Now that is y 1 minus y times, so let's compute matrix times this x vector here first. Then we get x minus 1 plus x. And in the second row, we get minus x plus 1 minus x, like this. So this is y 1 minus y, and 2x minus 1 minus 2x plus 1. So what happens here? Well, we get y times 2x minus 1 plus 1 minus y minus 2x plus 1. Or you could also say what we're getting here is 2x minus 1 times y, and then we have minus 1 minus y. And if we simplify that, we get 2x minus 1 and 2y minus 1. So that's the expected payoff. And what we can easily see here is that each of the players can force the payoff to be 0. If the column player selects x equal to 1/2, then the payoff will be 0, because then this factor will be 0, regardless of what the row player is. And if the row player selects y equal to 1/2, then this factor will be 0. So again, the expected payoff will be 0. So what we can see is that each player can enforce the payoff of 0. And they can do this even by using the same strategies, by choosing the strategy 1/2 and 1/2. Now what does that mean for the Nash equilibrium? Remember, the column player wants to maximize the payoff. However, the row player can force the payoff to be 0. So that means the column player will never get more than 0. Column player maximizes payoff as row player can enforce a payoff of 0. That means the payoff will never be higher than 0. So the column player can't win. The best thing he can do is not lose. And of course, from the other point of view, the game is just the same. It's kind of symmetric here. So the row player wants to minimize the payoff. He can enforce 0. Of course, he would like to have less, but on the other hand, the column player can also enforce 0. So that means the row player is never going to get less than 0. So row player minimizes payoff, and again, there's now the column player can enforce the payoff of 0. That would mean the payoff will never be less than 0. Now we just take these two together here. So we have a payoff that's never higher and never lower than 0. Then that means payoff is going to be 0. Otherwise, one of those two is always unhappy and can enforce 0, can do better by enforcing 0. Now in that situation, both enforce that payoff of 0, both play the strategy 1/2, 1/2 to enforce that point. No one has an incentive to change strategies, because if they do, the other player could exploit that. And that's basically the definition of a Nash equilibrium. So this shows we have a Nash equilibrium here. So the strategy is 1/2, 1/2, that's for the row player, and the same for the column player. That pair of strategies is in Nash equilibrium. And of course, that is precisely what you would expect. Both players should play both actions, 1 finger, 2 finger, with equal probability. Because if they don't, then the opponent will be able to predict that there is a higher probability for one of the two outcomes, and he'll be able to counter that. So for example, if the column player knows that the row player will play 1 finger with higher probability than 2 fingers, then the column player will also play 1 finger every time. And that means he'll win in the majority of cases. He will lose some, but the majority will win. If the row player plays exactly 50-50, then he wins sometimes, he loses sometimes, but in the long run, it will always even out to 0. And that's the basic idea here. So this pair of strategies, 1 over 2, 1 over 2, this is necessarily a Nash equilibrium. So this completes the introduction into matrix games. In the following videos, we're going to be concerned with how to actually compute a Nash equilibrium. You notice that we exploited a very special property of that game, and that is that both players can enforce a payoff of 0. That is, of course, not always the case. We'd like to have a more general strategy to compute a Nash equilibrium. We'll deal with that in the following video. And I hope I'll see you then.